Satellite communication. A body moving in an orbit around a planet is called a satellite. Moon is the natural satellite of the Earth. Artificial satellites are launched from the Earth for communication purpose and weather monitoring. These artificial satellites also orbit around the Earth in their own orbit. Let's see how the signals are transformed. After the artificial satellite is put into its orbit around the Earth, it starts to function. The signals are transferred to the satellite using the transmitter or uplink, and the satellite transforms the signal to the receiver or downlink. The time period for one complete orbital motion of an artificial satellite is equal to the time period of the Earth's one complete rotation. When an artificial satellite's orbit lies directly above the Earth's equator with a period equal to the Earth's rotational period, then it is called geostationary orbit. The satellites put in this orbit are called geostationary satellites. The satellites which orbit through north and south poles are called polar satellites. Polar satellites are used for weather monitoring.
EPIRB stands for Emergency Position Indicating Radio Beacon. They are distress beacons that tell Coast Guard you need help. How does an EPIRB work? The device contains two radio transmitters, a 5-watt and a 0.25-watt, each operating at 406 MHz, the standard international frequency typically signaling distress, 406 MHz. The 5-watt radio transmitter is synchronized with a GOES weather satellite going around the Earth in a geosynchronous orbit. The COSPAS-SARSAT is an international satellite-based search and rescue system founded by the US, Russia, Canada, and France to detect emergency radio beacons. Due to the many advantages of 406 MHz beacons and the disadvantages of the 121.5 MHz beacons, the international COSPAS-SARSAT program stopped the satellite processing of 121.5 MHz by satellites on February 1, 2009. Encouragements were given by National Oceanic and Atmospheric Administration /NOAA and FAA to switch to 406 for obvious reasons. However, emergency locator transmitter might still be used by aircraft, and alerts from these devices would not be acted upon unless confirmed by two other independent non-satellite sources or devices. An EPIRB transmits signals to the satellite. The signal consists of an encrypted identification number, all in digital code, which holds information such as the ship's identification, date of the event, the nature of distress, emergency contacts, and the position. A UIN is a unique identifier number programmed into each beacon at the factory. The UIN number consists of 15-digit series of letters and numbers that make up the unique identity of the beacon. The UIN is on a white label on the exterior of the beacon. The UIN is also referred to as the hex ID. The local user terminal, satellite receiving units or ground stations, calculates the position of the casualty using Doppler shift, which is the change in frequency or wavelength of a wave, or other periodic events, for an observer moving relative to its source. The LUT passes the digital message to the MRCC, Mission Rescue Coordination Center. Furthermore, the MRCC is responsible for the SAR ops and oversees the execution of the rescue mission. If the EPIRB is not compatible with a GPS receiver, the geosynchronous satellite orbiting the Earth can pick only the radio signals emitted by the radio. The location of the transmitter or the identity of the owner cannot be deduced in this case. These satellites can only pick up trace elements of such signals, and they can only give a rough idea of the location of the EPIRB. A signal of 406 MHz is treated as an emergency signal for international standards. The signal could help you locate the transmitter even if it is 3 miles away. The vessel or the individual in distress could be identified if the EPIRB is registered. If an emitter transmits signals of 121.5 MHz, the rescuer or concerned party can reach the lost person even if they are at a distance of 15 miles. The accuracy of reaching the target could be magnified if an EPIRB also contains a GPS receiver. Using an EPIRB, the EPIRB needs to be activated to emit signals by the beacon owner. This could be done by pushing a button on the unit, in the case of Category 2 EPIRBs, or it could happen automatically if and when it comes in contact with water through hydrostatic release. The latter is known as hydrostatic EPIRB. The quality makes it the best choice for sailors because it could be automatically activated in case the ship or vessel meets an accident and finds itself in deep waters. Battery. 12-volt battery. 48 hours of transmitting capacity. Normally replaced every 2 to 5 years. Use proper replacement battery. False alerting. The EPIRB might get activated by mistake by an individual on board and send false alarms. If the EPIRB is falsely activated, the nearest coast station or RCC, Rescue Coordination Center, must be informed immediately of this event and cancel it. The cancellation intimation must also be sent to the appropriate authority, for example, DG Shipping for Indian registered ships or ships plying in Indian waters when the false alert is transmitted. The ship owner and / or the agent must also be informed. Emergency position indicating radio beacon. EPIRB is a device to alert search and rescue services, SAR, in case of an emergency out at sea. It is tracking equipment that transmits a signal on a specified band to locate a lifeboat, life raft, ship, or people in distress. They are installed on ships and other vessels after being registered with the National Search and Rescue Forces to that boat. The registration allows confirmation of false alerts, faster and quick rescue operations in case of emergencies. An EPIRB is a secondary means of distress alerting, which is to say that it comes later in the hierarchy of alerting SAR authorities in case of distress. Types of EPIRB. COSPAS SARSAT EPIRBs under the COSPAS SARSAT system work on the 406.025 MHz and 121.5 MHz bands and are applicable for all sea areas. In Marsat E 1.6 GHz band is the one on which this EPIRB works. These are applicable for sea areas A1, A2, and A3. VHF-CH70 this works on the 156.525 MHz band and is applicable for sea area A1 only.
The system of modern 406 MHz satellite EPIRBs became operational in 1989. Designated as Category 1 or automatic and Category 2 or manual, these units operate on a dedicated rescue frequency to provide worldwide, all-weather distress signaling capability. The 1995 introduction of GOES, or geostationary Earth-orbiting satellites, gave the system instantaneous signal recognition from virtually anywhere on the globe. Today, activating a 406 MHz EPIRB provides authorities with all of the information contained on the owner's EPIRB registration and identification card within 6 to 10 minutes. Data from polar orbiting satellites gives them the EPIRB's precise position as soon as the satellites are in proper orientation. Depending on your location, this occurs within a period ranging from a matter of minutes to a few hours. An older system of Class A and Class B units broadcasting at 121.5 and 243 MHz remains operational. These are civilian and military distress frequencies that are monitored by satellites and aircraft. While the older units still work, They don't offer all of the benefits of the 406 MHz system. The older EPIRB system leaves large portions of the world entirely unprotected, and the shared broadcast frequencies suffer from interference and false alarms. Class A units no longer satisfy regulatory requirements and should be used only for backup. Class B units remain popular options, primarily as personal units for mariners whose vessels operate in covered areas. Before you rely on one of the older units, be sure you understand its limitations. EPIRBs are designated as either automatic or manual. Automatic units must be installed in a manner that permits them to float free from a sinking vessel. Once freed from the canister or mounting bracket, an automatic EPIRB turns itself on and assumes a correct operating position. Automatic units incorporate manual switches for activating or disarming the EPIRB. Manual units must be switched on by the user. In either case, the signal is relayed to a rescue coordination center. While the old 121.5 243 MHz system enables authorities to determine the location of an EPIRB signal, the more stable signal provided by the 406 MHz system provides greater accuracy and greatly improves the chance that you'll be found quickly.
NAVTEX, Navigational Telex, sometimes styled NAVTEX or NAVTEX, is an international automated medium-frequency direct printing service for delivery of navigational and meteorological warnings and forecasts, as well as urgent maritime safety information, MSI, to ships. NAVTEX was developed to provide a low-cost, simple, and automated means of receiving this information aboard ships at sea within approximately 370 kilometers, 200 nautical miles, offshore. There are no user fees associated with receiving NAVTEX broadcasts, as the transmissions are typically transmitted from the National Weather Authority, Italy, or Navy or Coast Guard, as in the US, or National Navigation Authority, Canada. Where the messages contain weather forecasts, an abbreviated format very similar to the shipping forecast is used. NAVTEX is a component of the International Maritime Organization / International Hydrographic Organization Worldwide Navigation. How NAVTEX works. The NAVTEX works on a frequency of 518 kHz in the medium frequency band. 490 kHz frequency is also used by some countries for broadcasts in the national languages, also known as national NAVTEX. Where medium frequency reception is difficult, transmissions are made on 4209.5 kHz. The default setting in a NAVTEX is 518 kHz. The entire world is divided into 21 areas known as naviries, including 5 areas recently introduced for the Arctic region, for the purpose of distributing this information. Each naviria has multiple NAVTEX stations, which further helps in transmitting the messages. Selection of stations. All NAVTEX receivers are programmable to enable the navigating officer to ensure that only messages from selected NAVTEX stations are displayed or printed. The selecting station menu under the menu option in a NAVTEX receiver allows the officer to select the desired stations he/she wants to receive automatically or manually. On automatic selection, the NAVTEX receives marine safety information for the area the ship happens to be in continuously and without any user involvement. If a ship's position data is fed from any navigating equipment like GPS, the NAVTEX will automatically decide in which naviria the ship is navigating presently and thus select the appropriate NAVTEX stations. In the manual mode, the navigating officer can select what stations he/she wishes to receive. A list of NAVTEX stations can be found in the Admiralty List of Radio Signals Volume 3 Part 1 and in the List of Coast Stations and Special Service Stations, List 4, for reference. Types of messages. The NAVTEX receives the following kind of messages. A equals navigational warning. B equals meteorological warning. C equals ice report. D equals search and rescue information / piracy and armed robbery. E equals meteorological forecast. F equals pilot messages. G equals ACE messages, formerly DECA messages. H equals Lawrence C messages. I equals Omega messages. J equals SatNav messages, GPS or GLONASS. K equals other electronic navigational aid system messages. L equals navigational warnings, additional. M to U equals reserve. V equals notice to fishermen. W to Y equals reserve. Z equals no messages on hand. The Navtex receiver can be set to ignore certain types of messages, however, messages A, B, D, and L because of their importance cannot be rejected by navigating officers. Audible alarms can also be generated when message type A, B, D, or L is received. It should only be possible to reset this alarm manually. We should also note that when programming the type of messages to receive, it is wise to ensure that only those which are required and necessary are programmed for the reception. Otherwise, a good deal of paper will be wasted or one will have to scroll through a mass of messages if the broadcasts are received in soft copy. The format of the message. The message in a Navtex receiver appears in the following format: ZCZC B1 B2 B3 B4 main message NNNN. ZCZC, it is the start code. It indicates the beginning of the message. B1, this character represents the station ID. B2, this character is called the subject indicator. It is used to represent the type of message. A to Z. The characters B1 and B2 are used by the Navtex receivers to reject messages from stations of concerning subjects of no interest to the officer. B3 and B4. B3 and B4 is a two-digit serial number for each message. NNNN. This indicates the end of the message. The characters B3 and B4 are used by receivers to keep already received message from being repeated. Below is an example of a message. ZCZC 0820. WZ 1593. Scotland, West Coast. The North Cardinal Light Buoy 58.01.2 and 005.27.1 W have been permanently withdrawn. Cancel WZ 1562. NNNN.
Volume 3 is divided into two parts, and you can go and find the two parts in the Admiralty chart catalog. So we are sailing in the Far East and Oceania, so we'll be using 2832. Once you open the book, in the index, the Navtex is shown, and it is in page number 40. So we'll go to 40. Navtex starts from here. So the Navtex will always be covering for different types of areas and different types of messages. So the types of messages are Alpha to Zulu, of which Alpha, Bravo, Delta and Lima. You can remember it as A, B, D, L. These are types of messages that cannot be rejected by the receiver. So all the other types of messages you can select on your receiver, and whenever a Navtex message comes, the first letters will be ZC, then B1 will be the transmitter identification, that's the station list. Next will be the subject, and the last two numbers will be the message numbers. So if it is coming from a station in area, maybe area 11, station is coming from Charlie and type of message is Bravo, and the type of number of message is 18, the number will be CB18. This is how you will identify the type of message and the station and the number of the message. And whenever the message is fully printed, 4 numbers will be printed at the end of the message. Navtex, how to update on the Navtex machine, I will show you in a later video. So if your ship is sailing, this is the list of all the Navtex areas. This list will give you the Navtex area, and in that area you have to select the station. So if you want to find out which all areas you are going to sail, suppose you are going from India to Singapore, just draw a line. So you will be going through X-ray 6 and X-ray 7. So we will go to X-ray 6. This is X-ray 7. So just give you an example of how X-ray 7 works. Suppose it is Mary. This is Mary. The station code is Tango, and the coverage is this. The coverage will be the circle which is having the same color of the Mary station. So if you are going to Singapore, you will be passing Penang. The color of the circle will be this. The station will be U. Then Singapore, station code is Charlie, and the color is this. So this is the circle that you will be getting messages from. This is how the stations are selected. So it's very simple. You find in the index diagram which all areas you want to navigate. Then once you go to that area, you will find the list of stations, and just select the station. And after you select the station, just select the type of message you need to receive. These are the list of types of messages that are received on an Navtex. And once you get it, take a printout. Some of the Navtex types have the provision to save the message without printing it. So you just save the message.
The GMDSS makes specific requirements with regard to radio equipment, and ships must be able to carry out several different functions, one of which is the ability to transmit and receive maritime safety information, MSI. Maritime Safety Information, MSI. Navigational reports, meteorological reports, weather forecasts, messages of general importance. MSI is transmitted via the FF. Navtex Inmarsat EGC system, radio telex, NBDP, radio telephony, safety messages. The Navtex system could reach up to a distance 600 nanometers offshore. 518 kHz is the international Navtex frequency. 24 Navtex stations in one Navaria. The 24 stations are divided into 4 groups consisting of 6 transmitting stations. Every group is allowed 1 hour transmission time. 10 minutes/4 hours. Navaries. There are 16 Navaries worldwide. Navtex stations are geographically separated. Every Navtex station has its own identification character, AZ. Navtex stations coverage is shown in the ITU list of radio determination and special service stations. Search and Rescue Radar Transponders, SARTs. Search and Rescue Radar Transponders, SARTs, are the main means in the GMDSS for locating ships in distress or their survival craft, and their carriage on board ships is mandatory. The SART is a small, battery-powered, omni-directional radar receiver and transmitter. They may also be incorporated into a float-free satellite EPIRB. The batteries fitted to a SART allow operation in the standby condition for at least 96H, plus a further 8H whilst being interrogated. Purpose and method of operation of a SART. A SART operates in the 9 GHz, 3 cm or X-band, radar frequency band and, on receiving a signal from a ship or aircraft radar, transmits a series of response, homing, signals. The SART can be activated manually or automatically, in some cases, so that it will thereafter respond when interrogated. The method of using and activating SARTs varies over the type available, but instructions are marked on the sides of all SARTs. These response signals will be seen on the ship or aircraft radar screen as a line of 12 dots, 0.64 n miles apart, extending approximately 8 n miles outward from the SART's position along its line of bearing. This unique radar signal is easily recognized and allows the rescue vessel or aircraft to locate the survival craft. As the SART becomes closer, another 12 dots are produced, also 0.64 n miles apart. See section 1.1.4. A SART will not respond to 3 GHz radar, also referred to as 10 cm or S-band, radar. Indication of operation and interrogation. On activation, the SART will provide a visible and/or audible indication of its correct operation. It will also provide an indication when it is being interrogated by radar signals from a searching ship or aircraft. Location distances. A SART should respond when interrogated by a shipborne X-band radar with a scanner height of 15 m within 8 n miles. A SART should also respond when interrogated by a compatible X-band radar fitted to an aircraft operating at a height of 3000 feet at a distance of at least 30 n miles. As height is the key to improving the distance that a SART will respond to a radar signal, survivors should endeavor to mount the SART as high as possible in a lifeboat or life raft, by lashing it to an oar, etc. Some models of SART incorporate mounting poles for this purpose. The vertical polar diagram of the antenna and the characteristics of the device will permit the SART to respond to radars under heavy swell conditions. SART transmission is substantially omnidirectional in the horizontal.
In the 9 GHz frequency band, generating a series of dots when being interrogated by a search craft with an X-band 3 cm radar. As the search craft approaches to within 1 nautical mile of the SART, the 12 dots change to wide arcs and eventually into complete circles as the search craft nears the SART.
Location errors. When a SART is being interrogated by a search radar, the SART's receiver is sweeping the radar band continuously. Search for radar signals. Once interrogated, or triggered, by an X-band radar in range, the sweeps becomes alternately slow and fast. As all marine radars do not operate on exactly the same frequency within the 9 GHz radar band, there may be a small delay in SART response as the SART receiver locks onto the searching radar signal. Once the SART receiver has locked onto the searching radar, there is also a delay as the SART switches from receive to transmit mode, and it continues to sweep. When the range closes so that the fast sweeps responses are seen, the first dot of the SART response displayed will be no more than 150 m distant from the true location of the SART. When the range is such that only the slow sweep responses are seen, range approximately greater than 1 n mile, the first dot of the SART response displayed will be as much as 0.64 n miles beyond the true position of the SART. Operating radar for SART detection. IMO Safety of Navigation Circular 197 provides guidance on using X-band radar for the detection of SARTs. This circular is included as Appendix 12. GMDSS carriage requirement. The GMDSS regulations require vessels between 300 and 500 GRT to carry one SART. or ACE SART. Vessels over 500 GRT must carry 2. The SART S, or ACE SART S, must be stowed in locations from where they can be rapidly placed in survival craft. Most Australian GMDSS vessels have SART stowed on the bridge, near the bridge wing doors. Alternatively, they may be stowed in survival craft.
So you've entered your survival craft, but now you need to be rescued. Even with ships searching in the correct area, narrowing down your exact location can be a real challenge. That's where a SART can help. They attract the attention of passing vessels by actually drawing on their radar screen. Activated correctly, it will point the searchers in the right direction, increasing your chances of being rescued. SART stands for Search and Rescue Transponder. It's an active device, meaning it transmits a signal to draw attention to itself. It's triggered when it detects a pulse from a radar. As soon as it does, it transmits multiple pulses straight back, painting a series of 12 distinctive echoes on the screen, guiding the searching vessel towards its location. They operate at 9 GHz, which means they show up on an X-band 3 cm radar screen. Day to day, the units themselves require very little maintenance. All you need to do is make sure they're clean and dry, check the battery expiry date, and test them monthly. Every unit is different, so you do need to check the instructions. On this unit, you can just slide the switch to the test position to temporarily activate it. It will indicate whether the internal test is successful, often with a light. If you have radar, you can also check the screen to check it's responding correctly. In an actual emergency, you need to make sure you take it with you. There's no rush to activate it, especially if you're still close to your original vessel. That will paint a large echo anyway, and may even block the SART's transmission. Once you are clear, you can then set it up. To activate the SART, you normally just need to remove a pin. It should then indicate to you that it's working. Once active, it needs to be mounted as high as possible. The higher it is, the further away it will be detected. In the water, you can expect only a mile or so. On the floor of a life raft, not much better, maybe 2 or 3 miles if you're lucky, but mounting 1 metre high, it must be able to be detected at least 5 miles away. 1 metre is the height of IMO performance standards, and it should have been designed to comply with that. SARTs have enough battery to last 96 hours in standby mode, that's 4 days, and 8 hours in transmission mode. Of course, it should only actually be in transmission mode when another vessel is close enough to detect it. If you have multiple SARTs, it's important to only activate one at a time. Using one ensures that the radar return maintains its distinctive nature and can't be confused with another echo. The other point to note is to never use a SART and a radar reflector close together. There's always a chance that the radar reflector will block the SART's signal. Once it's all set up, you just need to wait for a radar to be close enough to activate the SART. For the approaching vessel, the first sign that there's a SART operating is the characteristic dots on their radar screen. At long range, these show as 12 dots in a line, originating from the SART's location. The first return is the SART itself, and the further dots are the extra echoes generated by the SART. The extra echoes will be 0.6 miles apart, so they can be seen best on a 6 or a 12 mile range setting, as they will span a total of 7.2 miles across the screen. The precise range that the SART is first detected does vary. We've already spoken about the importance of mounting height. Another major factor is the height of the radar looking for it. For a surface craft with a scanner height of 15 meters, you can expect those performance standards of 5 miles for a correctly mounted SART. This then increases for bigger ships with higher radar scanners. The greatest range will be from aircraft searching around 3,000 feet. They may pick it up at even 40 miles away. Once the SART begins generating these extra echoes, it indicates to its user that it's under interrogation. Often this is by a flashing light or an audible signal. It tells the survivors there's an X-band radar operating nearby, and should act as somewhat of a morale boost. Knowing that there are vessels close by is also a good indication that traditional flares will be spotted. Even at maximum range, rocket parachute flares should still be visible to the vessel that has activated the SART. Hopefully, now the SART, or maybe even the flares, have attracted the attention of the other vessel. They can use the shape of the echo to locate the survival craft. As they draw nearer, the dots on their radar screen become arcs. This is because the scanner is picking up the returns across a larger angle. The closer it gets, the larger the angle that the scanner can detect the SART, so the larger the arcs become on the screen. Eventually the arcs become full circles, showing that the approaching vessel is now very close to the SART's location. If all goes well, the survival craft should be clearly visible, and survivors can be rescued. They're not cheap, but if you're